Hi. Just messing. Hi. Here, I want to give a little introduction to symbolic logic. Um, Logic is essentially the study of statements, just to define it very broadly. And so we should say what statement is. Or working, there are different ways to define it. But our definition of a statement is going to be expressions that can be true or false. Right? We don't have to necessarily know if it's true or if it's false. It just has to be capable of being true or false. So, for example, here are some examples of statements. Here are some examples of non-statements. And they could be in the domain of mathematics, or they don't have to be in the domain of mathematics. So, for example, if I say 7, that is not a statement because 7 can't be true or false. I'm not claiming anything about 7. I just said 7, right? Whereas if I say 7 is odd, that's a perfectly good statement. It happens to be true, right? Or I could say 7 is even. That's a perfectly good statement. It happens to be false, but it's still a valid statement, right? So though there are some mathematical statements and non-statements, but you can also have, in any language, it doesn't have to be in mathematics, right? So you could say something like, for example, the big car, right? That is not a statement. I'm not making any claim, right? But here I could say the car is big, right? That's a statement. It could be true, it could be false. And again, maybe it's up to opinion, right? Maybe some people think it's big, maybe some people think it's not big, right? But at least for some definition in some context of all of those terms, that it's a full claim that could be true or could be false, right? So this is the idea of statement or not a statement. Now, what I want to do in symbolic logic is we have our variables in symbolic logic. Typically, we use P, Q, R, etc. For statements, and they represent statements, which sometimes will specify specific statements that they stand for, and sometimes they just represent some generic statement that we want to work with. We also sometimes call them atomic statements. Sometimes we'll call them atomic statements, P, Q, R, meaning it's just a statement. And then we assemble them to form more complex statements or compound statements. All right, so compound statements are built out of atomic statements, say P, Q, R, etc., and logical operators. And what are the logical operations? So we have an operation called not, right? So it's written with a tilde, or sometimes it's written with a horizontal line, long horizontal line, and then a short vertical, right? These are not, or sometimes people call it negation, right? And this does just what you would think. If a statement P is true, then not P is false. If a statement is false, then not P is true. Right? And what I'm drawing here, this is called a truth table, right? It just shows all the possible values that a statement can take on, true or false. There is an operation called and, right? Or sometimes it's called conjunction. And this means that if you have two statements, right? P and Q, and you want to assemble the compound statement P and Q. Well, for the claim P and Q to be true, both P and Q have to be true. It's almost sounds like I'm just saying the same thing twice, but that's because our mathematical definition of and, our symbolic logic definition of and, it lines up beautifully with the English language definition of and that we use all the time, right? So say Q was false, well then the claim P and Q would be false. Say P was false, then the claim P and Q would be false. And if both are false, then certainly P and Q is false. There's also the operation or, right, which is also called disjunction sometimes. And it's written with this upside down. It's like and, but upside down. Or is a little bit trickier because we don't use or super consistently in the English language. There are really two different notions of or. There's inclusive or and there's exclusive or. So inclusive or means that you want one condition or the other to be true or both. So inclusive or is the type of or that you use, say, if you're specifying prerequisites for a course. You can take class C if you've taken class A or class B. Well, if you happen to have taken both class A and class B, certainly they're going to let you into class C because you've taken both. And you only needed one or the other. So you could sort of overdid the or there, right? However, we also in English frequently use exclusive or. Say you're talking to your kid who's already eating too much sugar and wants more dessert, and you say, okay, you can have a cookie or you can have ice cream, right? You kind of mean just pick one, right? You don't mean or both. So there's inclusive or, there's exclusive or. In symbolic logic, when we say or, we always mean inclusive or, right? If we ever mean exclusive or, we will specifically say exclusive. So this is always inclusive. If both P and Q are true, P or Q will be true. If either one is true, it's true. If both are false, then it's false. So that's the statement or. Then we have implies, right? Which sometimes we call implies, sometimes we call if then, and sometimes we call conditional. Right, these are all names for implication. And here you want to say, how could P imply Q? Well, if P is true and then Q follows, then sure, P implied Q. Right? If P was true, but Q did not follow, then P did not imply Q. Right? If P wasn't true to begin with, then we don't actually really care what Q was because we didn't make any claims about what would happen if P was not true. We're just saying if P, then Q. So if P is false, then it actually doesn't really matter whether Q is true or false. P implies Q is true either way. So these are sometimes a little bit, have a special name. These are sometimes called vacuously true. Vacuously true, meaning the implication was true, but only because the precondition wasn't present, right? So, it wasn't falsifiable. So there's one last symbol called the biconditional, or sometimes called if and only if. And this is, you're really testing the equivalence of two statements. You're saying, does the first cause the second, and does the second cause the first? Right? So this is sort of like equals in logic, right? You're saying, are the two statements equal, right? Are they equivalent? If they're both false, then you could say they're equivalent. If they're both true, you could say they're equivalent. Or if But if one is false and one is true, then you say that then it's false. The biconditional is false. So sometimes this is called if and only if, sometimes it's called biconditional. But the symbol for it is the double arrow, or the two-way arrow. So these are the basic symbols of symbolic logic, and how to write out the basic truth tables. So we use letters, P, Q, R, etc. for our statements. Then we have these symbols, not, and, or, implies, and if and only if. So that's the basic notation of symbolic logic. We'll talk more soon about how to assemble these into more complex statements and start making deductions, making inferences using these. Thank you. How's that?